Okay, today's lecture we're going to talk about inequity aversion. Still, we're gonna go a little deeper into figuring out what did these two economists, Fair and Schmidt, what were they trying to do with this model of inequity aversion? And what I was about to say is that they never call it inequity aversion in their first paper. The paper I asked you to read, the introduction to the world of inequity aversion, it was called, let's see what they called it. I'm going to go here and then share this. No, it's weird how they won't let me share what I want to share. This. They call it a theory of fairness, competition, and cooperation. And I think actually that's kind of interesting. I'm really zooming in here. I think you guys can see this now. Zoomed in, right? Um, if you want to know more about what were these guys thinking when they wrote this paper, just look at the title. The title tells you they wanted to tie together, they wanted to have one theory that made sense of fairness, the fact that people care about fairness. It made sense of competition, the fact that sometimes people aren't really caring about fairness, they're just competing with each other. It's like a cutthroat world to get what they want. And sometimes they cooperate. Um, and wouldn't it be great if we could have one theory that explained all three of those? And in fact, that was their goal. That's what they were trying to do. And it's called inequity aversion now. In the year 2020, which is 20 years after this paper was written, it's called, actually more than 20, I think it was 99. It's called inequity aversion because, admit, somebody's in the room waiting to come in. I think I pressed admit. Because that's the way to describe what's really going on in the model. Is it's actually people are averse, which means they don't like it when inequity happens. Whereas inequity is different people are getting different payoffs and not necessarily for any good reason. You know, it's not like we had a quiz and you got 100% on the quiz and I got a 60% on the quiz and I'm really angry that you got more points than me. I mean, I'm sure there's some people who feel that way, but that's not really an example of inequity, is it? Assuming assuming the quiz was fair, assuming the quiz gave everyone the same opportunity to answer the question correctly, I would say that's not an example of inequity, where you got 100% on the quiz, I got a 60%, and I'm angry about it. I wish we could just get everyone get 80s. Why do we have to take this extreme 160? Why can't we just all get 80s? I think we all agree that that's an example of inequality that is justified. It's okay that there's that inequality. But what if it was something else, like an experiment like the ultimatum game, where everyone in the room just simply volunteered to participate in some game called the ultimatum game, and half of them, just by sheer luck, by random chance, get to be the proposer of the ultimatum game, and the other half are forced into being the responder in the ultimatum game. And I've talked about this game enough. Hopefully you're familiar, very familiar with this game. And it says that the proposer can choose any distribution of, let's say, $10 that they want, and the responder chooses to accept or reject that proposal. Well, I would say this is an example of inequity. If the proposer says, I want $9 for myself and I'll give you $1, why are you getting more? Why is the proposer getting 9 and the responder only getting 1? It's that this person decided to exploit their position as the first mover and try to game the system and get some more dollars for themselves. And maybe they were just thinking, oh, the other person will accept $1 because what else are you going to do? Get zero? $1 is better than zero, so I'll offer you I'll offer you the $1. This is perhaps how the normal self-interested model of Homo economicus would say, I'll keep 9 for myself. I'll give you 1. You should accept because 1 is better than 0. So, hey, this is great. I get $9 out of the 10. What does this theory say? It says that because of inequity aversion, you got 9, I got 1. That's not fair. We both were participants in this economics experiment, and out of random chance, you happen to be the proposer, but that doesn't mean you deserve $8 more than me. And because of that inequity, I'm averse to that inequity. The way to avoid this inequity is to say, I'll reject the proposal. If everyone gets 0, there's no longer any inequity. Sure, I don't get the $1. I give up the $1, but at least I don't have to suffer from this negative emotional experience of having the inequity. So that's why it's called inequity aversion. Even though Fair and Schmidt, I don't know what Fair and Schmidt thought their theory was going to be called. Like, did they think people were going to call it a theory of fairness, competition, and cooperation for the rest of its existence? I don't know. They probably weren't thinking ahead that much, because that's not a very, doesn't roll off the tongue, I would say. Okay. Did you guys at least read the abstract? You know, abstracts are really great things. If you don't want to read a whole paper, you can get a lot of what's happening in the paper just by reading the abstract. This is like a secret of academia. You want to learn something but don't want to read too much, you can just look at the abstract, and at the very least, it'll tell you whether or not you need to read more to find out more about what happened in this paper. But that's this concept of the abstract. It's a nice summary of what was done and why. Okay, that chat, I don't need to read. Okay, did you read this? There's strong evidence that people exploit bargaining power in competitive markets, but not in bilateral. You know, that means just two people are bargaining. Strong evidence that people exploit free riding opportunities in voluntary cooperation games. What are they talking about there? Like public good games. They're saying that people exploit free riding opportunities in public good games. And remember, when I ask you about this, I mean that it may start out with maybe more than half people cooperating, but over time, the free riding effect kicks in, and most people just are free riding by the end of the game. When they're given the opportunity to punish free riders, stable cooperation is maintained. Although punishment is costly for those who punish. So, you know, standard economics says that shouldn't make any difference whether you have punishment, because no one will use it. Therefore, you can just ignore the punishment. That's not true. Punishment makes a big difference. People cooperate when there's punishment. This paper asks whether there's a simple common principle that can explain this puzzling evidence. Of course, it thinks there is. If people care about equity, well, there's the word equity. There's the inequity aversion. It's in that sentence. The second to last sentence of their abstract is really what they're, you know, that's how we know their paper. If people care about equity, that means if some people are inequity averse, they have inequity aversion, then this puzzle can be resolved. And it turns out that the economic environment determines whether the fair types or the selfish types dominate equilibrium behavior. That's something we haven't talked about yet. Why is it that in some environments, people tend to look fair on average? Like the ultimatum game. Ultimatum game, people totally look fair. The most common offer is 50%. And most offers are, 40% or higher in the ultimatum game. Looks pretty fair. Whereas in other games, like if you run a market game, lots of buyers, lots of sellers, there could be an equilibrium price that's predicted. And what do you find when you run these games? There's some noise. It's pretty noisy, but actually the equilibrium price, it converges to the equilibrium price pretty well. You could say, so what? What does that have to do with fairness? There's got to be some price, right? How could a market game What does it mean to be fair in a market game? Well, I'll tell you, and Fair and Schmidt will tell you if you read all of their paper. You can take a market game and change the supply curve or change the demand curve, right? If you take a market game and you shift one of the curves, either the supply curve or the demand curve, it doesn't matter which one. Hopefully, you guys know if you've taken any economics at all. Hopefully, you know that a supply curve and a demand curve together, where they intersect, that's the price. That's the equilibrium price, where supply and demand intersect. You can take an experiment and shift the curves. And what effect does that do? You would predict that changes the price in a market game. However, if people care about fairness, essentially about like splitting the profits from some trade, it really shouldn't matter too much. In other words, if let's say I have an item that's worth it's worth nothing to me, it's worth $0 to me, and it's worth $20 to you. If I sell it to you for a price of 10, then we split this profit. Wouldn't you agree? It's worth nothing to me. It's worth $20 to you. So I want you to have it. I mean, it'd be better off if you have it. It's worth more to you. But what price do I choose for this transaction? Well, if you both care about fairness, 20 for you, 0 to me, half of that is 10. So that difference, this sort of fair way to split up it's kind of like what's happening in an ultimatum game, isn't it? In an ultimatum game, you're splitting up usually $10. Usually $10 is being split in an ultimatum game between me and you, and I make an offer and you accept or reject. Well, in a market game, it's kind of the same thing, where I offer you a price and you can accept it or reject it. And the difference between what it's worth to you and what it's worth to me, that there's a name for that. It's called the trade surplus. So the trade surplus that's available for every transaction, you could think of that trade surplus as being split up. Like, how much do you get and how much do I get, right? That's in that sense, it's just like an ultimatum game. However, when it's in this market, people don't treat it like an ultimatum game. They really just don't. There's very few people have this idea of, well, we should just split the profits, whatever it's worth to you, whatever it's worth to me. Actually, what happens is there's competition. People are competing over price with if you're a seller, you're competing with other sellers. If you're a buyer, you're competing with other buyers. You're trying to get the most money you can for yourself in this market environment. And ultimately, the prediction of, let's see what they say. People exploit their bargaining power in competitive markets. Right. So that's the first sentence of their abstract. It seems that people exploit their bargaining power in competitive markets. This is what I was talking about. They don't say, well, it's worth 20 to me or 0 to me, 20 to you. Let's split the power. Let's split the money, 10 each. Rather, they try to exploit their position in the market. So if they happen to be in a position where you want to actually be on the short side of the market. So if there's if there's a lot of buyers but only a few sellers, what happens? The sellers have the power, don't they? That becomes a seller's market. If there's more buyers than sellers, then you can exploit your position as a seller and get more money. Or what if it's the reverse? There's only a few buyers, but there's a lot of sellers. Well, the buyers can exploit their position by getting a really low price in that case. And what the starting point of this paper, the very first sentence of the abstract says, there is strong evidence that people exploit their bargaining power in competitive markets. That's what I'm saying. When you do these experiments, people do. I mean, that's what we observe, right? If you're on the short side of the market, you exploit that fact to get more for yourself. But what about when it's just bilateral, when there's just me and one other person? That's the ultimatum game. Really, that's what they're talking about, the ultimatum game. Then you see people being fair. 40, 50% of the time, people are fair. I mean, 40 to 50% of the pie is offered. Okay, gosh, I'm going on for a long time here. But this is something we haven't talked about yet, which is um, the good thing about this paper is that it can do both at the same time. It can say there's a reason why. I mean, I should just tell you the reason, right? Sorry, this is really okay. So I mean, here's the model which I had on my slides earlier. This utility function, this is equation one in their paper. It tells you what the actual utility of a player is given a distribution of payoffs, not just my payoff, but what everyone's payoff is. Let's take a second to think about the difference between a market game. A market game where, like, say there's, 3 sellers and 10 buyers, and they're all trying to work together to get the price, or a bilateral game where there's just, ultimatum game, one buyer and one seller. What's the biggest difference in this equation between those two games? Is anyone willing to?
The N value?
The N value, exactly. I guess that was an easy question. But I bet a lot of people didn't understand even the question that I was asking. But thank you, Peter. In those bigger games, this N value is going to be larger. I described a game with 13 people in it. N would be 13 in that game. I don't know why I said 13. 3 buyers and 10 sellers, I think is what I said. But if there's just a bilateral game, N is 2. What effect does that have? If there's 13 other players, 13 players and 12 other ones, whatever this effect is, it's going to be minimized because of this. That's one effect, right? I mean, if I increase my payoff relative to you, there may be some envy or some guilt involved, but it will be divided by 12 in this case. 1/12 of that bad feeling will I actually experience. Whereas in just a 2-player game, N equals 2, 1 divided by 1 is 1. There's no division at all. It's the full negative feelings of the inequity get attributed to you. So that's one major effect, is that N is bigger in these market games. Okay, so what? Another thing is, remember, your utility depends on not just your payoff, but everyone's payoff. How many people's payoff can you affect in a market game? A game where there's three sellers but 10 buyers. So a lot of buyers, a lot of people want to buy your stuff. You are one of 3 sellers. How many people's payoff can you actually affect? Just one other person, right? What, 2? You can affect your own payoff and one of the other, let's say you're a seller. You're one of the lucky 3 who are sellers, and the unlucky 10 buyers all want what you have, but you have this power. You can exploit your position as somebody that is on the short side of the market. But how many people's actual number payoff can you affect? There's your own payoff and one other person, but everyone else you can't. Do you get what I'm saying here? When you make a deal with someone, they say, how about I sell this to you for, I know you guys really want it, so I want $18. Sell it to me for $18. And the guy's like, gosh, that's a lot of money. Okay, fine, I'll buy it. I'll buy it for 18. You've just made a transaction. How many people's payoff have you affected? There's your own, because now you get that, you sold that item, so you get the money from that. And there's the person who you sold it to. They get some payoff. Everybody else's payoff is not affected. In other words, most of these numbers here, these xj's and these xi's, xj is other people's payoff. It's down here too, xj, other people's payoffs. Most of those are fixed. You can't affect it. You can't change them. So whatever this effect here of inequity that you'd like to avoid, you would like to avoid inequity. You are just relatively powerless to fix the situation. there's still going to be inequity no matter what you do. The other buyers, they're going to get a lot of money. Let's say you're one of three. I'm sorry, buyers. I meant sellers. You're one of three sellers in this example that I'm giving you. There's still two others that are going to make a bunch of money, and you can't affect that. You're going to earn way less than them if you try to offer a more fair price to your buyer. Here's my
So,
point. Oh, do you have a comment? Go
so
ahead.
using that argument, monopoly is how we get rid of inequity.
Interesting. Monopoly is how we get rid of inequity. Are you saying that if there was just one seller, then they would be fair?
I'm being facetious, obviously, because it's not true. But yeah, if you have no competition, then your inequity aversion lets you try to make things more equitable.
That's an interesting question. I would say very good question. You got me in some sense that um, if you think about real life businesses trying to make money, I'm not sure this model applies. Do you know why? Because they're all profit maximizers. Almost every business that exists is a profit maximizer. The ones that aren't generally don't survive
I have
because,
worked for some businesses that are definitely not profit maximizers.
like, do you want to talk about it? Like, what are some?
I'm just fucking around. No, it doesn't matter.
Well, I mean, of course, you could give me some examples of places that, let's say they're socially conscious. That's an example, right? You could say there's a business who doesn't always try to make money. Sometimes they just try to do the right thing, and they have a reputation of being socially conscious. CONSCIOUS, that word. Um, yes, that's possible, and maybe ultimately that helps them exist. Comically inept. Yeah, that's true. Yeah, but my point, which was really to answer your question, is if there were fewer firms, would they be more fair because of inequity aversion? I think the answer is actually no. I don't think so. And then the reason is I have a different reason, which is not said in this paper, which is that um, real life firms tend to be profit maximizers. So we're not actually talking about firms. We're actually talking about individuals. I think this paper, it's not a great way to describe what happens with real firms, but it is a pretty good way to talk about what happens with individual behavior. Individual behavior can vary, right? That's what it started with in the abstract. I don't know if they said individual behavior. It says people. What do they mean by people? Or do they mean firms? Do they mean like the CEO of a firm? They're not really saying which people they're talking about here, but I think the best way to interpret this is to say people, individuals in their individual decision making behavior tend to behave this way. If you look at firms, I would say they're mostly profit maximizing. And they're sort of agnostic about this too. Which people are they talking about? Hmm. If you read this, you may see a little bit about it. They just mean people. They're not saying which people, just people in general. Um, but okay, I think I pretty much made the point that I want, which was that admit, which was that there's two kind of easy ways to see without even doing the math and like going through a bunch of examples, seeing why what they wanted this model to explain why the same group of people could look very fair in one environment and not so fair in another environment. Well, it could be because of the way that inequity enters their utility function as this divided by the total number of players, and also that it's if they can't actually control it, if it's somehow fixed. This is true of utility functions. If you change them by some fixed value, it doesn't matter. It doesn't change what you do. And so I guess that's my point. You guys have any questions about that? We'll talk more about that if you care. But that's one what I think is relatively straightforward way to see right off the bat how you can get what Fair and Schmidt wanted to get out of this. Of course, if you look at the rest of their paper, it's very long. They talk about the ultimatum game, what happens in ultimatum games, what happens in market games. They actually have a mathematical structure that would predict it using a rational choice model. They would predict, that's what this equation here is that says, what should the responder do in an ultimatum game? If they should accept any offer that's more than half. S is the share that you get in an ultimatum game. I'm just going to look at this proposition 1 right now and try to explain it to you. The responder, of course, should accept anything over than 1/2 of the share. That's nice. Thanks, you're going to give me more than half? Great, I'll take it. Or equal to half, they'll take it. But what if the share that's offered is less than 1/2? What if remember, they're the second player, they're the responder in an ultimatum game, and they get this S, which is less than 0.5. Well, I'm sorry, is S the share to the responder or to the share that's kept by the proposer? I should know this. The responder's share is denoted by S, and the proposer's share by 1 minus S. Okay, S is the share to the responder. They should reject the shared S if S is less than this expression here. Don't worry what that is. It's the 3-lined equal sign means it's identically equal to, meaning it's defined to be equal to this expression, alpha 2 divided by 1 plus 2 alpha 2. What is alpha 2 in this game? It's the alpha parameter, the one we've been talking about, that alpha parameter of the second player. That's what alpha 2 is. Remember, the 2 players could have different alphas. That's why you have a subscript, alpha 1 for the first player, alpha 2 for the second. What this proposition says is they should reject S if it's less than this amount. So let's say your alpha is 1. That's somebody who cares a lot about NB, right? 1. Alpha equals 1. Plug in alpha 2 equals 1 into there. You get 1 divided by 1 plus 2 times 1. That's a third. That's 1 divided by 3, right? A third. So what is this saying? If your alpha equals 1, then you should reject any offer less than 1/3 of the share of the total pie. And you should accept any offer greater than 1/3 share of the total pie. This follows mathematically from the structure. You know, equation one above this was the mathematical structure of this utility function. I would like it for us to be able to do this. People always ask me, how much math is there in your course? Well, not a lot of math, but there's going to be a little bit, and this is an example of one. And I think maybe the breakout rooms are the right way to do it because different people have different math backgrounds and abilities. And if I just do it myself, you guys are going to just sit there and do nothing. I mean, some of you will participate. But I think it'd be better for me to just force you to just have some interaction with some other person in this class, and breakout rooms are the way to do that. So what do I want to do? I want to give you a chance to use a formula like this, although in a slightly different way. I want to talk about the other direction. What do I mean by that? This is a proposition that says, all right, you tell me alpha, and I will tell you whether you should accept or reject the offer, right? For example, proposition 1 says, if alpha 2 equals 1, and the share is 0.4, then I should accept. Let me write that down. This is important. Okay. Oop, I don't want to just do to Zach. I want to do everyone. Okay, here is what is implied by proposition 1. If alpha equals 1 and S equals 0.4, then the responder should accept. I mean, and that's not the only thing implied by proposition 1. What did I do by this? I plugged in something for alpha, and I plugged in something for S, And I looked at this equation. It would say 1 divided by 1 plus 2 times 1 is 1/3. S is, no, sorry, S, it's not the case that S, which is 0. Let me write this out. Because 0.4 is not less than 1/3, we know that the responder should accept, right? So this is the final line of math that I didn't have. Look at the chat if you want to see what I'm saying, and that is this proposition. It's not like that enlightening, like, oh my gosh, we finally figured out the ultimatum game. Now we know what's happening. It's not that. It's a way for the Fair-Schmidt model to make predictions. It says, let's just say I knew what your alpha was. And I wanted to think about, if I know your alpha, what can I say about your behavior? What behavior would I predict for you in the ultimatum game if you're the responder? And this formula tells you exactly that. It tells you what sorts of behavior I should expect from you. Of course, I'm perhaps more interested in the other direction. And by the other direction, here's what I mean by the other direction. I'm gonna type in chat. The other direction is to observe how people behave in the ultimatum game, and then to infer. I'm gonna put infer in capital letters. It looks like I'm shouting at you when I type in capital letters, and then to infer what that person's alpha was. Check out the chat. I think that's actually even more interesting, and I think that's something I can ask you to do, which is, if I tell you exactly what people do in the ultimatum game, could you infer what this person's alpha was? Maybe by showing you this equation, I've made it too easy to do. But still, let's try it. I want to give you a question, and see if mathematically you can figure it out as a group. And that is, I'm going to ask you this. I'm going to ask you something I could ask on a quiz, right? So this is like, think of this as just practice for a quiz, except you have to do it as a group. You don't actually have to do it as a group, but I want to see if each group can come up with this answer. You know, maybe after a certain time, I'll just say, oh, never mind, forget about it. But I hope you do. I might reward you. Maybe I'll give you a point on the, on the homework you just turned in. Hopefully you turned it in. If you turned it in, you get some additional points on it. Okay, so here is the, wait, is there some way to share with each group? This is, I'm not sure about. Here we go. First of all, let me share this Word document, and that will give you the question that I want you to answer. Share. Here's a problem for the breakout rooms. What can we infer about the value of alpha of a responder? You guys see this? I'm typing it right now. What can we infer about the value of alpha of a responder who we observe has rejected? Let me be more specific over what this responder is doing. Of a responder in a, let's say a $10, I'm going to say ultimatum game. You guys know what a $10 ultimatum game is. The proposer has $10, they make an offer, the responder either accepts or rejects. Okay, so what can we infer about the value of alpha of a responder in a $10 ultimatum game if we observe that the responder always accepts any offer above, I'm going to say $2, and they always reject any offer below $2. Okay. This is the problem I'd like you guys to answer. I'll try to make it available for you. You might say, what do they do if it's exactly $2? Um, um, I don't think it matters, but let's say they accept. Above $2 or equal to $2. But let's say they always reject any offer below $2. That includes including like $1.99. So let's say this ultimatum game has a penny involved. So it's like really accurate here. We know exactly how this person behaves. If you give them $2 or more, they accept it. If you give them $1.99 or less, they reject it. Some of you may already have the answer to this question, but let me just put you in breakout rooms for once and see what happens. And stop share. I'll try to share that with you. What's happening? Maybe I can't do breakout rooms. Oh, yes, I can. Okay. Create rooms. Open all rooms. Is there some way to force you to go to the rooms? Hello, guys.
Hello.
Do you need the problem again? Can you see the problem?
I can't on my end.
Do you want me to
No.
repeat it?
Sure.
It's an ultimatum game for $2. If I type here, can you see it? Responder accepts any offer above $2. What is his alpha? Okay.
Oh, okay.
Can you
Cool.
see that chat that I just said?
Yes. Thank you.
Okay. Try to solve this problem. I want you to tell me what the alpha is, and if you do, I'll give you I don't know, maybe one or 2 points on your homework. Okay.
Cool. Thank you.
Okay. Hello, guys.
Howdy.
Do you understand the problem? What?
Kind of, sort of.
Do you
I
want me
guess
to,
I'm
do
not
you want me to
really
chat
sure how
it
to
to you
answer.
again?
No, we have it up. We have it up.
You have the
I think,
problem up?
Oh no,
yeah,
we have the paper up.
If I chat this, will this help? The responder accepts any offer above $2. What is his alpha? You see that?
yes.
Okay. So the answer you should tell me is the alpha. Say alpha equals blank, and that will be the answer. And I'll see if it's right or wrong. If it's right, you guys get a free point on your homework. Okay? Hello? Are you guys still muted?
Yeah, we got you.
You're not working together, are you? I'd like for you to try to work together. That's the whole point of these groups.
Yeah.
Okay. Well, good luck.
Nice.
Hello, guys.
Oh,
Do you understand the problem? Do you want me
Yes.
to chat
Yeah.
it to you again? I can
Yeah.
chat it to you again, just as a summary. The responder accepts any offer above $2 and rejects anything below $2. And I want you to tell me what this person's alpha is. So the answer will be alpha equals a number, and you have to tell me the number. And if you get the right number, I'll give you an extra point on your homework. So you care. I want you to care. You understand? It's a math problem. Do you have any other questions? Need any other help? before I go on to the next breakout room?
I think we're fine.
All right. You guys talking to each other?
Yeah,
Great.
I think it was Peter. He's quite helpful.
Well, I hopefully want
Explaining
you
it.
all to talk. Don't just listen to Peter.
No, we're working on it right now.
Okay, awesome.
All right,
Good luck, guys.
thank you.
Hello, guys. Do you guys understand the problem?
Not really.
Okay, let me explain it to you. The problem is, assume that there's a responder. If I type here, assume there is a responder in a $10 ultimatum game, and that person accepts any offer $2 or greater, and they reject any offer $2 or smaller, I should say. Reject any offer smaller than $2. You have to find out what that person's value of alpha is. So if you can find their value of alpha mathematically, you find out what it is, and tell me, you get a point added to your homework. That's your incentive. I want you to care a little bit. So you use the Fair-Schmidt model to think about what can we say about a person in terms of their alpha if they reject anything less than 2 and accept anything more than 2. They must have some alpha that causes them to behave that way. Your job is to figure out what their alpha is. Are you guys not talking? You're certainly not going to get anywhere if you don't talk. I can't force you to talk. I can't force you to have your video on, but that was the goal here, was to do some breakout rooms so that people would interact somehow. But I'll come back to the breakout rooms and see if you have an answer later. Do you guys understand the question?
So are we using the utility function that we spoke about the previous lecture? Or are we using what you just spoke about, proposition 1? Because that's where I'm getting confused.
It's the same utility.
Yeah.
It's the same one. Yeah, it's the Fair-Schmidt inequity aversion model. The same thing we've been talking about last class and this class. I don't get your question. Are you asking, did something change that we're talking about in proposition 1? No, proposition 1 is just a detail that you actually don't need to know. You can ignore proposition 1 if you'd like. This is a mathematical question. It has a math answer. You should tell me what alpha is. Let's say you think alpha equals 3.5. It's not 3.5. But if you thought alpha was 3.5, you could tell me, and then it should be that anyone with alpha equal to 3.5 would behave exactly this way. That would reject anything below $2, and they would accept anything. If you get that right, that's the right answer. You know what I'm saying? You can even check yourself. Whatever you think the alpha is, you can plug it in, let's say to proposition 1 if you want, or just sort of do the math yourself and say, is it true that this type of person would reject this offer and accept this offer? And if so, then you can be confident you got the right answer. I admit it's kind of hard, especially because it's the first time you're doing this. But I thought maybe the group environment would help. Do you understand the question? Syed says yes. Michael says yes. Is there really some reason you guys can't unmute? Are you somewhere that's really loud?
No, I'm good. Sorry about that.
You're in a private breakout room. I think it'd be easier for you to talk to each other with words rather than chat. I mean, if you only use chat, you can. But Syed, you understand the question. Michael, you understand. Are you good? I want to give you some
Yeah,
time.
yeah. We'll unmute and we'll figure out the answer. Yeah, sorry about that.
Okay. Well, it sounds like you understand the problem, and good luck. If you need more help, you know, text me or something. I'll be around.
All right, thank you.
All right. Bye. How's it going? Did you see my message? Let's end at 1:30.
Yes.
Okay.
Yeah.
Do you guys already have an answer?
Um, yeah, we basically just came up that A would be greater than or equal than 2 since you said the responder didn't want to accept anything or only accepted offers above 2. But yeah.
So you're saying alpha equals 2?
Is greater than or equal to 2.
Well, I will. Here's a hint. I don't want greater than or equal to. I want you to tell me alpha exactly.
Like a number?
Yes.
Could you put the function so we have to use that function then to okay. Can you type that out too since we can't see that in the chat?
I'm sorry. Type what out?
The function.
What function?
Well,
The utility function?
yeah, isn't that what we would need for the thing?
Okay, so the utility function, I'll try to type it out. Utility equals your own payoff minus alpha times utility equals your own payoff minus alpha times the difference between your payoff and the other person's payoff. This is how I would say it in words. I don't know if that's what you mean. Does that help? I don't have a good math editor in terms of the chat box, so I can't put in a bunch of symbols, but I
So
can say it in words.
is alpha just saying what the utility is of what you're asking for? I'm confused on.
So alpha is a parameter.
Yeah.
Let me send a message to everyone.
Okay.
Maybe other people don't. If you don't understand what alpha is, that's a problem because that's kind of the whole point of this.
Yeah. I mean, I get it a little bit.
Alpha is a parameter, and I'm asking you, what is this person's parameter? What is the alpha parameter of a person who would behave this way? So let me leave the room. I'm going to send a message to everyone.
Hey, Professor, are we?
Are you done?
we've been done for a while. We just didn't know when, like, are we leaving the breakout rooms or are you going to pull us up back out?
You can come out on your own.
Okay, I think maybe send a message to people because I thought you were just going to pull us out.
Oh, okay. Well, you should chat me your answer for the group. Maybe no wait. Maybe I'll go to the group and I want to send everyone a reminder. Alpha is a parameter that you are trying to find. The responder's utility function is equal to their own payoff minus, oh, I can't send a longer message than that? Oh no, it's limited. Darn it. Okay. I don't think I can send this message. Okay, so who else was in your group, Peter?
Ibrahim and Sierra
Thanks.
and Zachary.
Yeah, I got that.
Hi, Professor. Are we still in breakout rooms? I'm a little confused. Or I see.
No,
okay, I
when
see
you're
7
done, when
participants.
you're done, come back to the main room.
Okay. All right. Yeah. I went back and forth, and the participants were the same, and I was a little confused. But I see
Oh,
now
sure.
it's 7.
When you're done, just come back to the main room. How about that? And send a private chat to me. Private chat me your. Maybe I should go. I didn't go to the rooms, but can you just can you say I don't have a good way for you to answer other than private chats. Okay. Yeah. I already got that was group 1. No, that was group 3. I already got your answer for group 3. Syed, that's your answer for group 4. Okay.
I just want to clarify
Yes.
something for the question.
So I need an answer from groups 1 and 2 when they're ready. Sorry, what?
Can I have a clarification?
Sure.
Yeah, in the question, you're saying that the person would reject 2 but would accept 3.
So they would reject $1.99, but they would accept 2.
Oh, okay.
Yeah. So groups 1 and 2. I think I'm going to close the rooms. Did group 1 and 2, did you get it? Anyone here from group 1 and 2? I don't think they got it. I only think one group got it.
Can you hear me by any chance?
What's that?
Oh, can you hear me? My audio was acting up. What group? I'm not aware of which group I was in.
What's your name?
Oh, this is Nick.
Nick, you're in group 4.
Oh, okay. Sorry.
Did you get private message me an answer?
Okay. Okay.
I already got yours, Ibrahim, your groups, but thanks. Group 4. In group 2. This is really hard to, you're getting, I'm getting different answers from different people in the same group. So yeah, I probably should have gone to your group and then got your answers, but I want to go through this and show everyone how to get it. Yeah. Sorry, I don't think group 1 got it. But that's okay. I want to now show everyone how to do this problem. I think it'll make sense. I think it'll make sense. It appears that group 4 got it. I'm a little suspicious because I got the wrong answer from group 4, and then later on I got the right answer. So I want to know how you got that, Michael. Half of us left, half of us stayed and solved it. Should I believe you? So who were the half that stayed? Okay. Let's see. Let me write that. Okay, so let me go over the right answer to this and show everyone in all groups like how you do this problem. It's a math problem. It's not a hard math problem. I think you'll see very quickly, very easily. So let me share a whiteboard. I'll do it on this. Pretend it's a whiteboard. All right. Good job to the groups who got it right. 2 groups got it and 2 groups didn't. That's okay if you didn't. I think, maybe this is confusing because it's the first time I've asked you to do something like this. So I don't know. Okay, so here's the problem. If I give $2 for myself and $8 for the other person, I'm gonna put this in parentheses as an outcome. This has to give me the same utility as if I reject and get 0 and 0. How do I know this? So this here is accept, and this is reject. These 2 things have to give me the same utility because it's right at my indifference point. I will accept anything that's $2 or greater, and I will reject anything that's $2 or less. So if you don't want to put 2,8 here, you could put 199 and 7 or no, sorry, 199 and 801. It really doesn't matter. The point though, and I hope everyone can get this, is that you should accept any offer that gives you at least $2 or more, reject any offer that gives you $2 or less, and if you get exactly $2, you don't care. You're right on the edge of where you would reject it or accept it. And that's why the utility, I'll put a U here for utility. The utility of getting $2 for yourself and $8 for the other person is equal to the utility of getting 0 for yourself and 0 for the other person, because that's what it means to reject. Can everyone see that? If you accept, you get 2 and they get 8. If you reject, you get 0 and they get 0. Now you have to figure out what actually is my utility if this happens. If I get 2 and you get 8, the utility function is equal to my own payoff, which is 2. That's the first thing in the utility function, is my own payoff. And then I subtract from that alpha times the difference between these two payoffs, which is 6. Alpha times 6. Maybe I should put 8 minus 2 there, just really show you where it comes from. You would have seen this in the video too. If you watch the video, it's exactly how I calculate utility. That's what you get if you accept. What if you reject? What utility do you get? You simply get the utility of 0. If you reject 0, I'm sorry, if you reject, you get 0, they get 0. There's no inequity, so I don't have to subtract anything. I'll write it here just in case you want to see. Minus alpha 0 minus 0, but that goes to 0, of course. That goes to 0, of course. These two utilities have to be the same. What do I get here on the left side? 2 minus 6 alpha is equal to 0. This is what we can infer. We can infer for this person, 2 minus 6 alpha, that's the utility they get if they accept, is equal to 0, that's the utility they get if they reject. When they're right on the edge, when they're right in between where they want to accept and reject, this should be true. And I have to solve this for alpha. You can like add 6 alpha to both sides. You get 2 equals 6 alpha, and then divide 6 by both sides. You get alpha equals 1/3. So the answer was 1/3. Okay. How do I know the answer is 1/3? I used what I knew about the Fair-Schmidt utility function, this inequity averse utility function. It says if I keep $2 and the other guy gets 8, how much actual satisfaction in the form of utility do I get? It's 2 minus alpha times the difference. It's 2 minus 6 alpha. What kind of utility could I get if I reject? It's 0 because of this. And if my behavior is that $2 is the minimum I need to accept, that means these two utilities have to be the same. And therefore alpha has to be 1/3. Do you guys have any questions about this? Like where this comes from? Do you understand how I got to this answer of 1/3? The key is to understand this equality right here among the utility functions. You know, I didn't come right out and say it. You sort of had to figure that out. You could have used the formula in the paper, proposition 1, but you really didn't need to. If you understand this equality here as a, the minimum I need to accept is when the utility I get from accepting is equal to the utility I get from rejecting. That's where all of this math comes from. So if I give you a different question, you can still use this principle. You can still use the principle of, well, if I know some point that's indifferent between somebody where, like, let's say the minimum acceptable price is blank. That means that's the lowest price I would accept before saying, nah, I don't want to buy the thing at all. This is the same concept. You can set those two utilities equal to each other. Or in a trust game, right? That's not the best example. In a trust game, let's see, the second mover is deciding how much to split up between how much to give back to the player. If I told you how much they gave back, okay, so that wouldn't be an equivalence here. You couldn't use this accept equals reject because there is no sort of minimum offer that I would accept. It really is more of a, you can use exactly this argument in a sort of a minimal acceptable offer situation. Say, well, in the minimal acceptable offer, my utility must be equal for whether I accept or reject it. Okay. Do you guys have any questions over any of the math that's going on here? I kind of feel like I should go back to the main room. Where is it? Stop share. Okay, here we are. I do have some slides on this, so I think next week we'll do this some more. You can actually just see the slides that I created for this. For example, I want to talk about the dictator game. I want to talk about what can we infer about people's, not their envy, but their guilt, right? The reason you reject an offer in the ultimatum game is envy. You don't like the fact that other people are getting more than you. But why do you give money in a dictator game? It's not envy, it's guilt, right? You don't want to leave the other person in a situation where they got very little and you got a lot. So I think next class, because we don't have time to do it this class, we're going to do the same thing. What can we infer about beta if we observe a certain behavior of the dictator? And of course, if you want to, you can go ahead and read about it in my slides because I write about it there. Yeah, so we'll do that next class. We'll do that Monday. But I think that's it. I think Monday will be the last day that we go over this model of inequity aversion. Let's not have a quiz on it yet. We'll push the quiz back. I feel like we just had a quiz. So we'll Monday of next week, we'll finish this up. And then on Wednesday, we'll talk about behavioral game theory. I like that topic a lot too. Learning about the differences between the way people play games with each other, how they actually play games with each other as compared to what game theory predicts. There's a few things I want to talk about there. So do you guys have any questions about? I think a lot of the groups at first they didn't know what to do, but it seems like 2 of the 4 groups got it. To the groups that didn't get it, I hope you're not too dejected about this. It was kind of a hard problem in this. Actually, mathematically it wasn't hard, but you had to get this idea that, oh, I can set these 2 utilities equal to each other. I can know the fact that the utility of rejecting should be equal to the utility of accepting right at that minimal acceptable offer. And I didn't tell you that. You had to sort of figure that out on your own, or use the equation from proposition 1. But that was in a different form, wasn't it? It was like alpha over 1 minus 2 alpha. You had to sort of do the inverse of that. That said share and alpha over 1 minus 2 alpha. If you plugged in s equals 0.2 and solved for alpha, I'm not sure if you would have got the right answer. Would you have? Let's do that really quick. If s equals 0.2 equals alpha over 1 minus 2 alpha, would you get the right answer? Did anyone do that? You did that. Did you get alpha equals 1/3?
Yep.
Really? Oh, maybe I have the wrong formula.
It should be 1 plus, not 1 minus.
1 plus 2 alpha? Okay, so you get, if alpha equals 1/3, you get 1/3 over 1 plus 2/3. That's 5/3. You get 1/5, which is equal to 0.2. Yes, it's the same formula. Thank you, Peter. It does work. If you had just used that formula from proposition 1 and plugged in s equals 0.2 and solved for alpha 2, you would have got the answer as well of 1/3. So there were many ways to attack this problem. I don't want you to feel like you somehow are terrible students if you didn't get this problem, because it wasn't easy. And this was just practice. This was just getting you used to even hearing problems like that so that you'll be able to do it on a quiz or an exam. Hope that's okay. But good job to those of you who got it. I think that's it. I think I'll see you guys on Monday. You don't have homework for Monday, so party all weekend. Get ready to vote, or if you haven't already. Any other questions? Yeah. It was tough using the breakout rooms. A little tougher than I thought it was going to be.